Welcome to this machine learning case study. Today we will be covering the paper titled Modeling Phytoremediation of Heavy Metal Contaminated Soils Through Machine Learning by Shi et al. Phytoremediation uses plants to remove toxic heavy metals and metalloids from soil. The ideal plant species to use for this process are hyperaccumulators, which are species that concentrate high amounts of contaminants. The goal of this paper was to use machine learning to predict factors that affect phytoremediation of heavy metals and the importance of each factor to the process. For context, potentially impactful factors to phytoremediation include species, plant metal uptake mechanisms, plant physiological characteristics, soil physiochemical properties, agronomic practices, heavy metal physical and chemical properties, and environmental and experimental factors. To prepare the dataset, data was obtained through a systematic literature review using Google Scholar and Web of Science. Input data included plant family, environmental conditions, soil properties, and metal properties. Output or predicted data included shoot heavy metal concentration, shoot yield, bioconcentration factor, which is the ratio of heavy metal concentration in the plant versus the soil, the ratio of metals extracted from the soil, the time it took to remediate the soil, low molecular weight organic acid production, which are acids that are secreted by plants and can act as chelators and impact heavy metal bioavailability, and relevant gene expression that include those that encode for chelators and heavy metal transporters. To pre-process the data, they first used k-nearest neighbors method to fill in missing data within the set, and then used one-hot encoding to turn categorical features into a one-hot numeric array. The dataset was then split, with 80% of it going toward hyperparameter tuning and model training, and the remaining 20% going toward testing the model's generalization ability after it was trained. Two models were developed for this project. The first was extreme gradient boosting, or XGBoost, which corrects and combines decision trees for regression predictive modeling. It was used to make multi-label predictions of shoot heavy metal concentration, shoot yield, bioconcentration factor, metal extraction ratio, and remediation time. The second model developed was an artificial neural network, which uses artificial neurons to evaluate input data, find patterns, and make classification predictions. It was used to predict low molecular weight organic acids produced and gene effects on heavy metal phytoremediation mechanisms. The performance of the model was then evaluated using 20% of the remaining dataset. The regression model was evaluated using the determination of coefficient, or R-squared value, and when that value is closer to 1, that indicates a better prediction, and the root mean squared error, or RMSE value, which, if that value is smaller, that indicates higher accuracy. The classification model was evaluated using the accuracy score and the F1 score. The project also evaluated feature importance, which is the score assigned to input features that reflects their usefulness in target variable prediction, and feature correlation, which is the relationships between features. For the regression model, feature importance was calculated based on performance improvement measured by the Gini index, and correlation was evaluated through integration with the partial dependence plot tool from Python. Within the classification model, feature importance was determined by the Shapley additive explanations, or SHAP method. Now moving on to results. For the statistical analysis of data acquired, looking at the average heavy metal concentrations in milligrams per kilogram within the soil samples, nickel displayed the highest average concentration, followed by zinc, then copper, then arsenic, and finally cadmium. The coefficient of variation, which is the variability within the heavy metal concentrations, indicated that the metal accumulation within the soil was due to anthropogenic activities. Moving on to the average heavy metal concentrations in milligrams per kilogram within the hyperaccumulator samples, nickel again displayed the highest average concentration, followed by zinc, then arsenic, then cadmium, and finally copper. Looking at the bioconcentration factors for each heavy metal, arsenic displayed the highest mean, then cadmium, then nickel, then zinc, and finally copper. During the development of the regression predictive model, the data underwent log transformation to redistribute it into a normal distribution. The performance evaluation was then looked at before and after this log transformation and hyperparameter adjustment. As you can see from the evaluation metrics, the log transferred data performed better within the model than the original data. The authors also graphed the predicted values and the test values, and they found that the concentration of predicted and test points on the y equals x line indicated a high model prediction accuracy. Now for interpreting the model, the authors found that the heavy metal chute concentration in micrograms per gram was most impacted by the metal properties, followed by experimental conditions. Plant yield in milligrams per plant was most impacted by experimental conditions and then soil properties. And the bioconcentration factor, metal extraction ratio in percentage, and the remediation time in years were all most impacted by plant family, followed by experimental conditions. Now for the evaluation of low molecular weight organic acid production and gene identification. The model performance was based on optimal hyperparameters, and as you can see for the acid production, the F1 score and accuracy of the training set was higher than the accuracy and F1 score of the test set. But for the gene identification portion, the accuracy and F1 score of both the training and test sets were very similar. They also looked at the impact of each input feature on acid output and gene expression, finding that plant family Brassicaceae, soil pH, and plant family Asteraceae had the most impact on acid production, and plant family Crassulaceae, Brassicaceae, and Asteraceae all had the most impact on the genes expressed within the hyperaccumulators. The authors concluded with saying that the most important features for phytoremediation were plant family, experimental conditions, soil properties, and heavy metal properties. The plant family Crassulaceae had the highest potential for hyperaccumulators. The metal ion radius is the most impactful factor on chute heavy metal concentration. And finally, that the developed machine learning model can predict soil remediation performance and be used in future phytoremediation experimental design. If you're curious to learn more, here's the full citation of the paper. Thank you for watching.